This is our presentation on Markov chains.
Matrices. A matrix is a rectangular arrangement of numbers into rows and columns. Matrices are used to represent data in mathematical equations. For example, matrices are commonly used in electrical engineering and computer science. Matrices describe a system of linear equations or transformations.
A transition matrix is used to help explain a Markov chain. It is a method for modeling and analyzing systems that change over time, and they're really good at representing the management of inventory and logistics, the impact of marketing on customer behavior, monitoring population dynamics, and modeling transportation systems. They are a representation of transitions between different states, allowing for predictions of future states. And specifically, they identify long-term trends and recognize steady states, which we will explain later. The setup of a transition matrix is the rows are the states from which the data is transferring, and the columns are the states to which the data is transferring. The element of a transition matrix is the proportion of the transition from one state to another and is between 0 and 1.
Markov chains. A Markov chain is a sequence of random variables where the variables are predicted only based off of the one immediately behind it. A Markov chain can be described as a transition matrix from one period to the next. Suppose that we have a Markov process with M0, M1, M2. M of n is the distribution across states at date n. M1 equals M0 times t because M0 is the distribution at date 0 and t is how people transition across states within a period. So therefore, multiplying one by the other gives you the distribution of where they end up in the next period. Since m of 1 equals m0 times t, m of 2 equals m1 times t, we can sub in what we know m of 1 equals, and we get m of 2 equals m0 times t squared, and m3 equals m0 times t cubed. And we can generalize this to say that m of n equals m0 times t to the n.
Here is a Markov chain that explains the situation that we have. So Ella started with chocolate ice cream, Avia started with strawberry ice cream, and I started with vanilla ice cream. Here it shows that the chance of Ella staying with chocolate ice cream is 70%, the chance of her going to strawberry ice cream is 10%, and the chance of her going to vanilla ice cream is 20%.
And here I started with chocolate, so I have a 70% chance of staying with chocolate ice cream, a 20% chance of switching to vanilla ice cream, and a 10% chance of switching to strawberry ice cream, which was shown in the diagram.
I started with vanilla ice cream, so there's an 80% chance I'll stay with vanilla ice cream, a 10% chance I'll go to chocolate ice cream, and a 10% chance I'll switch to strawberry ice cream.
Since I started eating strawberry ice cream, there's a 30% chance I switch to vanilla, a 30% chance I switch to eating chocolate ice cream, and a 40% chance that I stay eating strawberry ice cream.
Here we have another situation with the three of us where Ella started off sleeping, I started off running, and Avia started off with ice cream. So this Markov chain shows that I have a 60% chance of continuing to run, a 10% chance of sleeping next, and a 30% chance of going to ice cream next.
Here everyone is where they're starting at. So Avia has a 10% chance of staying with ice cream, Daisy has a 60% chance of staying running, and I have a 20% chance of staying sleeping.
Since I started eating ice cream, there's a 20% chance I go to sleep and a 70% chance that I start running.
I started sleeping, so there's a 20% chance that I'll switch to ice cream and a 60% chance that I'll start running.
And since I started with running, there's a 30% chance that I'll go to ice cream next and a 10% chance that I'll sleep next. Here we have another situation of inflow and outflow between states, but with TV companies. Here, a city has two cable TV companies, Cablecast and Best TV. Each year, 40% of Best TV customers switch to Cablecast, and the other 60% stay with Best TV, and 30% of the Cablecast customers switch to Best TV, which means that 70% of Cablecast stays with Cablecast, and that is shown in the Markov chain below. And then on the right is the Markov chain as a transition matrix, with the rows representing the states where we start and the columns representing where we're going.
Steady state distribution. The steady state is when you have m of n and multiply it by t and you stay at m of n, and you always stay at the same state. For t to the power of n, when n goes to infinity, you get the steady state if every state can be reached from any other state, which means from A you can get to B or C, from B you can get to C or A, and from C you can get to A or B. And if the chain is not periodic, which means the number of steps it takes to reach another state can't be a multiple of an integer more than 1, meaning if you're at B, you have to be able to get directly to A, not to C, then to A. If these two contingencies aren't met, then we don't have a unique steady state. You can either have infinite or just multiple. In this example, we have a transition matrix T and a Markov chain X and Y to find our steady state. We take the Markov chain and multiply it by T, and we get a system of equations. The last equation, x plus y equals 1, comes from the fact that every row in a Markov chain has to add up to 1. When we solve this system, we get that x equals 1/3 and y equals 2/3. If we plug that back into our original matrix and multiply it by t, we'll always get 1/3 and 2/3.
Markov chains in medicine absorbing state. Here we have 3 different states, healthy, sick, and dead. And 60% of the people who are healthy will stay healthy. 30% of the people who are originally healthy will get sick. And 10% of the people who are healthy will die. Also, 20% of the people who are sick will become healthy. 40% of the people who are sick will stay sick. And 40% of the people who are sick will stay dead, become dead. All of the people who start dead will stay dead because it's an absorbing state. In medical Markov chains, dead is an absorbing state, which means once entered, the probability of leaving the state is 0. Since all the other states have a percentage going to the dead state, eventually everything will end up there.
This is our transition matrix of healthy, sick, and dead, or healthy, sick, and dead. And this is our M0, or the person in the first period who is completely healthy. And to figure out what he will be in the second period, you take M0 and you multiply it by the transition matrix. And then doing matrix multiplication, you'll get 0.6, 0.3, and 0.1. And then this will be M1. So to find M2, you take M1 and multiply it by T. So now in period M1, this person will have 60% chance of being healthy, 30% chance of being sick, and 10% of dying. And then if you take M1 and multiply it by T to get M2, or state 3, you'll get 0.42, 0.3, and 0.28. So then in state 3, or state M2, this person will have 42% chance of staying healthy, 30% chance of being sick, and 28% chance of dying.
Medical Markov models are used to estimate life expectancy and survival probabilities, compare treatments by changing transition probabilities, predict people's health every year, and help doctors make decisions using data from large groups of patients. And this shows the impact of medical Markov chains.
In conclusion, Markov chains can be used to predict and track any kind of pattern, as the future state depends on the current state. They are essential for understanding complex systems in various fields, such as health patterns in the medical fields. When Markov chains are represented as transition matrices, you can predict the immediate future of the pattern based on the period right before it. This is our bibliography.
Thanks
Thanks for watching.